All right, so I'm Artem Chernyak. I work as a staff software engineer at Horizon Investments, which is an investing company out of North Carolina. I work remotely, obviously, since I'm here in St. Louis. And this talk is going to be about using Rust to make Python really fast. So first thing that comes to mind here is when I say that we're going to use Rust to make Python fast. First off, fast is a very relative term. It can mean a lot of things to a lot of people. I'll show you exactly what it means in this context. But also, when you think of using a language to make another language faster, you oftentimes think of like huge library rewrites and things like that are a major engineering investment just to speed things up, right? Like polars, redoing pandas, like millions of lines of code being written just to do this speed up thing. So first, let's define what I mean by fast here. What I mean by, whoops, that went the wrong way. What I mean by fast is faster than Numpy. So this is a library that I wrote as a little hackathon project. It does not support all of Numpy operations, obviously, but supports some of the most common ones. And as you can see, it's about twice as fast as Numpy. And the base program was about 50 lines of code. So when I say that it supports a subset of Numpy, I really mean a subset. So this is what the benchmark kind of looks like. But this is actually for a use case that we use at work, which is we do a lot of financial simulations. When you run financial simulations, you end up running a lot of operations on dictionary-like data sets. You end up running a lot of operations on them. The data sets usually aren't huge because, right, you have like certain assets and things like that. You end up with kind of smallish data sets that you're running things on. You're not talking about like millions, billions of rows. You're talking about like hundreds at most. So this is what the benchmark looks like. We start off by creating a data structure, just populating with random UUIDs, generating random numbers in it. Start our performance test. Then we use numpys from iter that can grab that dictionary, transform it into a vector in numpy, because numpy requires everything to be a vector. It requires you to transform into a native data structure. And then we run this for loop for testing that does scalar addition, so where you see the array comma 4, that's adding 4 to every single number in there. When you see the add for x and array, that's doing an element-wise addition of two individual vectors. It's adding them together element by element at each indice. Then the subtraction, multiplication. So everything pretty clear here, right? Any questions on the benchmark?
Yes, but I'll ask them later.
No, ask them now, please. I have way more content than we have time, so please ask questions.
Okay, so I mean, you also have to factor in the fact that Python for loop is also extremely slow, right? Because like for underscore and range, that's calling like 3,000 operations underneath the hood, and you have that performance there saying, okay.
Right. But if you run every single benchmark this way, right, we're testing what's inside the loop.
So you set it up. For loop still has overhead.
Yeah, but you pay the for loop overhead for every single benchmark.
Every
single benchmark runs like this.
Okay.
We just replace.
No,
you can't see the laser pointer. Okay. LCD screens. Anyways, yeah, the add, subtract, multiply operations. That's what we're really benchmarking here.
Okay. No, because like you would run in the same for loop for the.
Exactly.
Okay.
Because the for loop carries over, it's just overhead of running the benchmark. So it does not impact the performance that we see up there.
And just like to make sure, you definitely tested it in a bunch of different ways.
Yeah.
Yeah.
All right, so how did we start? So as I mentioned, we run a lot of these operations. Oh, thanks. Will that? No, the LCD screen just eats it.
Oh, maybe it's the angle. Does it work from back here?
I don't know, but yeah.
Oh, no.
Yeah.
That's
So
all.
yeah.
It's gotta be direct on.
Yeah, that's crazy.
I got one that shows up on screens, but that's in the tank bag.
I don't want to ruin their stream either with something that powerful. So how did this start? As I mentioned, we run a lot of these operations, right? And as everybody that works in data science, we were using pandas for a lot of this. So, but we noticed something really weird here. When we were running like this million operations on a tiny little array, all of a sudden, that time shot up to 120 seconds with pandas, which is insane. Before you saw that none of the Numpy benchmarks went over 2 seconds. Pandas hitting 120 seconds. And these benchmarks are done in the exact same way as the ones above in the for loop. They're using a pandas series, not even a data frame. We were using data frames, so our benchmarks were an order of magnitude slower than even this. And yeah, it made us ask what the hell. So we looked at polars also. As you can see, polars performs a little better, but it's still nowhere close to the Numpy numbers. And then we asked, what if we just try to do this in Python? So we literally ported some of the operations to Python, right? Like everybody can follow this, right?
Yeah.
Little dictionary comprehension, doing scalar addition, doing addition item by item with a dictionary get. And to our surprise, it actually beats polars for the small data sets with lots of operations. It runs faster than polars.
Is Black Bear, once again, that's your...
Black Bear is my coworker's library that does all of this in pure Python. I was going to call this talk the Battle of the Bears, but
Good.
but yeah, so for those small operations, we're actually beating out polars, we're beating out pandas, we're performing really well with just pure Python. The problem is when you get to those larger data sets, and we have a mix of those. So when you have a mix of those, you end up having this like Frankenstein code base where part of it you use one library, but then like at a certain breakpoint, you got to switch your libraries to do things. Otherwise, you hit this huge performance decrease. So I wanted to see if we could make this better by unifying it with Rust. Since polars is written in Rust, I was like, what if we simplify some of the bounds checking and things like that polars does and do a dirty library? And that's what you saw above. So to start a new project in Rust, you can actually use UV tools to install Maturin. I think that's the library name. This is actually a Python library that takes care of the binding and building of the Rust crate in a Python-friendly way. So you can install that. You can do like Maturin new red bear. See, another bear. Yeah. So we start the red bear, we CD into the project, and you can actually go ahead and generate a CI workflow. Oh. So Maturin takes care of all the packaging for you. If you generate the CI workflow, it includes testing on all the major platforms, Windows, Linux, Apple ARM, all of that stuff. And it creates a pipeline that also does deployment for you if you provided the keys and things like that. So just everything's taken care of for you. So Maturin is great. It's based on PyO3, which is what we'll be seeing a lot of later, but this is the basic setup. And you end up with a small little project like this. So you have your cargo toml, have your PyProject toml, and you have your source library. We'll be focusing, all of our work will be going into that lib.rs, but the cargo toml is the same thing as a PyProject, includes all the dependency management, all the library information, things like that. Any questions so far?
So Maturin is just like a environment setup tool,
Basically.
setup tool.
Basically, yeah. You can run Maturin develop, and it does like automatic linking and compiling. Like when your Rust code recompiles, it will link it to the Python binaries and get everything rolling. Yeah. All right, so let's start with our scalar function. For those, how many people here have not seen Rust at all? Cool. No, it's good. It's good. This might be a little bit of a blur. It's going to be a lot of Rust, but at the same time, it shouldn't be anything super surprising. So we're importing hashmap, which is the equivalent of a dictionary, and we're importing everything from PyO3 prelude, which is just a common Rust pattern where instead of importing like a bunch of different modules, you just expose everything through this prelude, makes all the functions available, makes it so that we don't have to include macros like this. So Rust has macros. This is a procedural macro, so it ends up being a function that wraps your function and does a lot of nice things. In this case, what the Py function here does is it will automatically take your hash map, or take Python's dictionary in this case, turn it into a hash map. It will take that value of float 64. If you pass it any type of Python number, integer, float, anything like that, it will turn it into a float 64, which is just a sized float. And then when you return a hash map, it will take that hash map and turn it back into a Python dictionary. And all of that is just taken care of for you. So you write almost pure Rust with a few macros and it ends up becoming Python, which is really cool. So then how do we do this? It's not much more complicated than the comprehension we saw. We need to run into iter, which takes the hash map and transforms it into an iterator that you can then run functional operations on, such as map. We map over it, and mapping over a hash map will give you a tuple. If it returns a tuple, it will build up a new hash map by using those key value pairs to build up the hash map. And collect is the part that actually builds it up. The reason why you need collect is because iterators in Rust are lazy. I'll get to it in a second. They're lazy, so they'll do stream processing on the whole chain. That way you don't if you have a bunch of, let's say we had 3 map operations here, you won't actually loop over the list 3 times. You'll feed in each element through a stream, and then collect is the part that actually turns it into that final data structure. Yes, question?
What happens if you don't pass in like a Python data structure? And also you just return a custom Rust data structure?
You're calling it from Python though, right?
Yes.
So what do you mean you don't pass in a Python data structure?
Like it's either it's a custom design like class object or something, or if it's like or you're returning a Rust structure.
Yeah, we'll get to that.
And
We'll
real
get to
quick, to
that.
make sure I'm understanding what's happening, so this is allowing it to be accessed from your Python code. Is
Yeah, so you
that
just
Python?
do
Yeah.
Yes. Add Taylor as an
What's the
importer.
overhead of
Like,
Py
literally.
function?
That's cool. Actually, that's
The overhead of what?
Have you tested the overhead of Py function, just
Okay.
like testing via time?
Yes, and we will
Got it.
see that in a second.
Okay.
So there actually isn't a lot of overhead, but there is a natural overhead of conversion, and that can be steep.
Yeah, there's a whole section on it.
Yeah,
In
yeah, and we'll get to that. And I hope. I'm sorry. This is, like I said, this is a lot longer. If I run out of time, I might do part 2 at the Rust meetup because I have 61 slides, and we're at 10. So yeah. Okay, so this is a more complicated example. Some of the things Rust doesn't support is providing like default values into your function, right? The nice thing about Python is you can say, like, for example, for this one, if fill of 0, like default to 0, if you can't find a value in the second dictionary that we give to add. Makes sense in Python. In Rust, you have to use a macro for it. So you, once again, use the Py function, then you do Py03 with a signature, and the signature allows you to do defaults and make it more Pythonic. They are currently working on allowing you to do some type hints in there, because the type hints don't fully translate to Python yet. But that's kind of a future enhancement. But for now, it's literally like an untyped Python signature. It supports most of the things you'd want to do in there. And then what you end up here is your fill just ends up coming in as the 0, 0 or whatever gets passed in. All of it gets worked out magically. This should look familiar. Just 2 hash maps returning a hash map. The one thing I wanted to mention here is that we are doing a clone. So since Rust does not have a garbage collector, we have to manage the memory manually. And when we use that key to create a new hash map, we have to essentially clone it in order to make sure that it's a separate key from the one that the original hash map had. Otherwise, we can't convert it back into a dictionary cleanly. All right, is this pretty clear? So
because you said the operations are lazy, so the iterative and the map, they don't run until you call collect.
Exactly. And then finally, we have to create a Python module. So Rust has its own module system, so you can drop this in the middle of the file. You create a Python module by creating a new Rust module. So mod redbear creates a Rust module. You use a Py module macro to wrap it and does all that stuff. And then inside it, the use super, so super is the module above it. So the functions we saw before all live at the top level of your file or your module that automatically gets created as a file. And then this module is inside your module. So super just calls out to them, imports your add scalar and your add, and then you do a macro that does Py module export to make sure that those functions get exported to Python. So everything's private by default. You have to explicitly export.
You mentioned typins earlier.
Yes.
You just like write your own like PyI files for these?
You can.
Okay.
And right now that's the preferred way, but they're trying to incorporate it more because it would be nice to keep those close to the code. I personally hate like separate type files because they just tend to get out of sync and just a pain. The less files I have to jump around, the better. All right, so that looked pretty good, right? Unfortunately, when we ran that, performance was just not there. If you look at that, so those conversions that I mentioned that you asked about are really freaking expensive because every time we call one of those functions, we do the conversion between a dictionary to a hash map and then from a hash map back to a dictionary, and those really add up. And you can see, so remember Black Bear was the native Python one. So this is way slower, like 4x slower than native Python. So did we just waste our time here? Well, conversions are the expensive part, as we said. I won't spend a lot of time on that, but the way we minimize conversions is we take inspiration from Numpy. What Numpy does is you can't just pass it Python data structures. You have to convert it to a Numpy data structure first and then work with that data structure. So by taking inspiration from this, we should create our own data structure so that we only have to run our conversion once and then be able to reuse the data structure. So how does that look in Rust? Well, we can create a Py class, which you wrap around a struct. You tell it that this will be a class essentially, and the from Py object does some magic to let a Python object get converted to the structure back and forth. Then it has a single values, which is a hash map of string f64 as we saw before, but it's wrapped in an arc. An arc is a smart pointer, so it does reference counting. What this essentially allows us to do is we no longer have to convert the hash map because this stores a pointer. When we're passing it back and forth, it only converts that pointer. So it only converts a number, which actually doesn't even need conversion. So we eliminate all that conversion back and forth because it's a pointer, and we pull the hash map out from Rust from that pointer inference, right? You can think of memory as kind of, I see some confused looks, so I'm explaining it.
I do have one quick question.
Yeah.
So is the data saved in memory in the form of a Python dictionary? Are you able to just like read that directly?
No, so in this case, it's saved as a hash map in Rust's memory. It's saved as a hash map. The pointer just says that this thing allows you to index that hash map somewhere in memory.
So do you still have to transfer the data from the Python dictionary to the Rust at that
You no
one
longer
time?
do, because this is an enclosed object. You are only transferring the pointer. So only that value that says this is an index like 1, 2, 3, 4, you're only transferring that pointer that says that this is an index 1, 2, 3, 4. You can just pick up the data structure from memory whenever with that
So
index.
it'll like convert the struct and the Python object that the struct has almost nothing, it's just the pointer?
Exactly.
Okay. Okay.
What's your guarantee that the original Python dictionary in memory resembles a hash map? I guess that's where I'm getting lost.
Yes. So, well, there is no guarantee anymore.
Yeah.
Yeah, there is no guarantee because you're converting it to a hash map and you're storing the hash map in memory. It's a hash map now. So to start off, you're working with a hash map going
Oh.
forward.
Okay.
Yeah,
So
Yes.
are you converting a Python dictionary
Sacrificing
to
some
a
memory.
Rust
Yeah.
hash map once?
Yep.
And now whenever you're doing operations, you're just
Operating
carrying
on
that the pointer values.
exactly.
Okay, so
There
then
is a standard.
Oh, I guess
Rust
before were you
standard,
doing that
so-
conversion on like every operation in that earlier method?
Every time you called it.
Oh. Okay.
Yep. So now, yeah, we can implement methods too, because we declared that struct is a class. So in Rust, you do this impl syntax for structures where you can implement things on them. Normally you do this for traits, but you can do like an empty one that does a non-traded implementation. And then we get a method. This should all look familiar. I'm only going to cover add here because it pretty much translates. Yeah, we just grab the values now. Since it's a smart pointer, Rust automatically takes care of everything for us. We do the iterator, we do the map, we collect it, and then we just do, so yeah, so all those selves, they're just same thing as reddict, just easier not to type it, because I've renamed it a couple times and I got lazy. But yeah, and then we just wrap it back up in our data structure and let the library take care of everything. And that gets us faster than Python. That little change. So now we're beating pure Python pretty much linearly. Very similar approach. But it's not quite enough. We want more. If there are any questions, like these benchmark slides are a great time to ask. So feel free.
Is the only significant change from the last benchmark slide to this one that number of times you're converting your data structure?
Yep.
Okay.
All right, so the other thing is the way we were building up the structure where we were mapping over it and letting the hash map build, Rust and most low-level languages, actually most high-level languages too, whenever you build up a data structure element by element like that, they have to essentially take the data structure of 0 and then grow it and then incrementally grow it, and they have to keep track of like when to grow it and all things like that. And that becomes really slow. So our signature stays exactly the same. Now we use our friend clone. You remember we cloned a key before. Now we're cloning our whole values structure. Because this compiler can get really well optimized with this because this is an operation it expects to do a lot. And we can trust it to be really fast at this. So we just let it do its thing, be as fast as it can. Then we do an arc make mute to make our values mutable. This is a lot of Rust boilerplate. If you don't understand it, it's okay. Just remember that mutation helps speed things up. We do an iter mute, and then for each, we dereference the value. That's what the star is. And we mutate it by adding on the value that we grab to it. So we're no longer pushing new keys onto the hash map or anything like that. We're just mutating what's already there with our super efficient clone already cloned for us. And then we're wrapping it in this data structure and giving it back. And that made us about twice as fast as Python. So this, or actually twice as fast as we were before. So that's a big improvement. Yes?
were you cloning the individual keys beforehand, and is that why it was slow?
It wasn't the cloning of the key. Partly it was the cloning of the keys, but the bigger part was that we were building up the hash map from scratch, right?
Okay.
because it
So
was
is this
built up
alloca-
from
is
an
this the
iteration.
allocation overhead because you're like every single time you're adding
Y-
elements, you're
yeah.
controlling.
Yeah, every time it reaches a breakpoint, it will reallocate and it'll create a new hash map that's slightly bigger and then slightly bigger and slightly bigger.
Okay.
Yeah, and that's why we just clone it up front, run our things. Yep.
Okay. Because if it's just a clone, it's a fixed size, you know how big you do.
Exactly.
Okay.
So this is pretty good. This is pretty good. But we can do a little better. So we can ditch our hash map. If anybody here is familiar with data-oriented design, when you talk about hardware architecture in a computer, when you talk about like CPU operations, right? Obviously, byte and numeric operations are the fastest, the lowest. Like plus is the fastest thing you can do, and one of the fastest things you can do on a computer, other than like a bit shift. The next step up is you're basically grouping numbers and bits, right? And you group numbers and bits with vectors. So CPUs and general hardware architectures are very optimized for vector operations, especially if you give it one continuous vector. So we change our reddict here to have an index hash map and then a vector of the values. So what the index hash map does is it takes each key and it maps it to an index in that values vector. That way, when we do like scalar addition, we do that addition to the elements of the vector. We never even touch the indexes. We don't even care that it was a hash map at one point. We work with the vector itself. And adding elements to the elements of a vector is super freaking fast. So how does that change our code? Well, now we get to answer part of your question, is how do we know that this still represents a dictionary? And we can write our own init method. Yes?
So I was busy taking pictures, so I kind
Yeah.
of blanked out. So at in the last slide,
Yep.
you had everything, all of your values are stored in one array, and that index is just saying, okay, it's going to start here, and then when you do the operations, you're only doing the operations in one array.
Yes, on the values array. Well, the index maps the keys to where they are in the vector,
Yes.
right? Because hash map is unordered,
Yeah.
so we can't keep
Yeah,
the
we need
order.
that if you're like doing access, so if you just want to do some operation on your array.
Yeah.
Wow.
All right, so this is another limitation of Py03. You actually, turns out that Python's init method is very magical. So they don't support init. They support the new dunder method. If you're unfamiliar with the new dunder method, it's really not meant to be run. It's like a low-level implementation detail, but it works the same way as init. It runs right before init, though. And you can do all the same things with it. So Py03 uses that.
Interesting.
Honestly, I tried to research it. I tried to see if there were any drawbacks to it. I could not find any. So yeah, so I don't know why Python has two. I couldn't get a good understanding of
I
it.
think if you want it to be named, you can make new return an object of a different class.
Oh, okay.
That would be
New-
disgusting.
There you go.
New in Python is a class method, so it doesn't operate the instance.
All right, so you remember how I said that sometimes like these things have to grow? Well, you can prevent them having to grow by using with capacity. So with capacity says that I know for sure my vector will have this size, but I do not know what elements it will have where yet. And you can do the same with hash map. And it just allocates that memory for you, pre-allocates it, makes it nice to work with. We probably could have gotten a little bit of a speed up by doing some of this in our previous iterations, but it's kind of pointless because we're moving on here. So we're doing this with capacity just to make these things a little bit faster. Then we do a for loop, which look very familiar. We're doing enumerate on our dictionary, which ends up giving us position and key value pairs. The position is just the order from the enumeration. We don't care about the order because it'll be unordered in the index anyways, and we can just push the values into our vector. So we go ahead and do that. And then we just return our structure mapped, all wrapped in our arc pointers. Is that all pretty clear?
So Actually, this is more of a Rust question, but for the self return there
Yeah.
at the bottom, is that just like the sort of a new struct syntax, but with self?
No.
Not the class.
It just
Basically,
means
I'm returning-
red dict.
Yeah, I'm returning.
Yeah, I get that. I was just wondering like why you have to use the self.
You don't have to. You can use red dict if you want.
Oh, okay.
Yeah, I just prefer.
Well, it's
Yeah, like I
better
said.
shown.
That is more clear.
Yeah.
You save 6 bytes.
Don't you have RSI?
No, for me, I prefer it because I rename things a lot.
Yeah.
So that way I don't have to rename red dict in 15 places.
Well, also if you're implementing something with like a complex lifetime or a generic parameter, it might automatically include that as well.
Okay, good to know. Thanks.
And you might save like 5 bytes or 7 bytes
important.
instead of 3.
I mean, the renaming things does seem like a pretty good reason, because like
Yeah.
now you just don't have to rename it in two places.
Dry trace the whole thing.
Yeah.
So back to our functions. So scalar add, I'm going back to scalar because this changes things a little bit. We're gonna keep all of our lessons learned, so I won't bore you guys with talking about mutation again. So we do the self-clone right away. Here though, notice we do the self-clone on the entire data structure. Because both are arc values though, we get just pointers to both the vector and the hash map. Because the hash map never gets modified in this class, the hash map just stays a pointer through this is where the power of that arc really comes through, right? We never touch it, we never convert it, we never read it. It just stays a pointer, and arc just keeps it as the same pointer. So it just flows on over, 0 overhead. Then we do our arc make mute on the new values. We run it on the values only, and we do the same thing, dereference value, add value to it with modification. And we return our new duplicate.
Does this one get converted? This is the thing that gets converted back into a Python object?
Yep,
Okay.
Oh,
that's self, that red dict.
Okay.
The whole thing gets converted, pointers stay pointers. And just for completion's sake, this is our add. We do kind of the same thing. We mutate new, we mutate our new values, and then I do a for loop over the indexes. I have to do it over the indexes because we have to look up the keys in the new dictionary because we don't know if the order stayed the same, right? So this is where we get our right-hand value. So from the other hash map, we index it, we get it, we map over it to extract the values, and then we unwrap it. And finally, we take our new vals and we add to it. That's pretty much it. And that actually starts to beat Numpy. We're still slower than Numpy on some of those bottom operations, but we're getting close.
Which one's red gray? Which one's not fine?
The light gray.
So it's they're both light gray.
The top a lighter gray.
Which one's NumPy?
Okay, NumPy.
NumPy is the bottom one.
This one's NumPy.
Yeah.
So would it keep scaling like that? Like no matter how, like the larger the operation, the larger the number of operations, what is that? A small number of operations on a huge number of things, generally you're gonna get a speed up with
Yeah.
this method. But when there's 1,000 operations, each one has some overhead that NumPy is getting ahead on.
So right now we're getting an overhead on the elements, more so than the operations. We actually eliminated our overhead on the operations. But if you notice, we're falling behind when we get to a lot of elements.
Oh, I'm sorry. I think I had these back. That was 10 elements in 1,000 operations.
Yeah.
That's why ops was on the right side. You know, in retrospect, it's obvious, but I
It's
had
all
these
good.
backwards this entire time.
It's all good. So to figure out what we can do here, we need to look at this example. So this is how you use reddict. I know it took a while for you to see the actual usage, but this is the final usage. So you import radbear. I have it imported as RB. Sorry, didn't include the import. And then you do rb.redddict to transform into your redddict. And then you can do your add scalar, add, things like that, all in that for loop. So this is something that Numpy benefits from that we're not. If you notice here, we are using the same base dictionary that we're mutating. And even when we're adding it to itself, we're still using the same dictionary. And because we're cloning the whole object with the key map and all of that, what we actually end up doing is every one of those dictionary iterations, all of them have the same order of elements in the vector. So if we end up with an identical index, we know that our vector has the same order, right? Because if the index is the same, we know the same keys map to the same values in the vector, so we can just add the two vectors. We don't even have to do any lookup. That's what I mean here. The code will actually help explain it a little bit. I know that words can sometimes be hard, as LLMs have shown us. So again, if new index is the same as other index, and Rust is efficient in production mode, it's actually going to compare just the pointers, and these end up with the same pointers, so this comparison is super fast. It doesn't even do an element by element comparison. It just sees that the pointers are the same, and then it knows that it can work with the vectors. So it's super efficient the way we have it cloning. And then in here, we do a zip operation with the other values iterator, right? So we get our left hand and right hand. We only modify our left hand, and that's it. We just modify the vector by traversing two vectors with a zip. And that's what gets us to be faster than Numpy. So,
explain the last part again?
like the whole part?
Yeah.
Yeah. No, yeah. Well, because this must be this is the magic of getting it way faster.
If you're comparing the new.index, other.index, and you're saying it's comparing the pointers, right? I'm thinking in C you can do pointer comparisons, like pointer equality.
Yep.
But that means they're fundamentally they're the same object.
Only the index is the same object. Our redddict consists of an index and a vector. We split them out. So the index can stay the same as long as our vectors stay the same.
Was the index your key vector?
Yeah, it was the key hash map. It was the hash map that mapped the keys to the indices.
And so that's never altered, I guess, because all your operations are just on the right hand side.
Exactly.
But okay, so the indices are the same objects, but the vectors on the
But the vectors mutate per instance.
And so is this putting your so this whole step is like putting those two vectors back together into a Python dictionary?
No.
Okay.
This step is just iterating through both the vectors, like zip, right, lets you iterate element by element, like in the same order. So it just takes first elements, adds them, puts that in a new vector. Second elements from both adds them, puts it in the new vector, and then gives you that new vector. Or not even gives you a new vector, but just modifies the left one.
Yeah, I've used a lot of like Python iter tools.
Yeah.
These look very familiar.
So you're skipping the key checking of
Yep.
the second one, basically.
Well, the key checking and the retrieval, right? Those are pretty expensive operations when put together, because you're not only doing a lookup in the hash map, you're then doing a lookup in the vector by the index from the hash map value. And we can skip all of that because we know that the vectors are in the same order as long as the index stays the same. So that's the magic trick.
Oh, this is all in the app. Oh, I didn't see that.
What
Yes.
kind of keys are you usually using for
So-
these values?
So this is specifically with string keys.
Okay.
I was going to explore like supporting other keys or going a little further here, but honestly, like this supports a lot of use cases already. And if you need to do that type of thing, like it works. If you have mostly simple operations, which a lot of the times that is what you need and have.
Yeah.
So this only
Cool.
operates based on if you're adding two dictionaries together.
Yeah.
And I love it, it's because you've set things up so you just don't have to check where you are it's like you've ordered things already together, so you're just doing like this single operation add between them. That's great.
What is the NumPy equivalent of adding two dictionaries of values? Like,
Add. It's just add. You pass it to Sirius and you
But
add them
since they're
together.
unordered, you have to like check and move everything around. So if you pre-order them or like set them up in the right order, then you don't actually have to check anything.
well, with NumPy, you're just adding two vectors together, right?
Yeah.
I actually don't know.
Yeah, so that's why that's basically why we have to do this, because NumPy has that optimization kind of built in. Like it doesn't have to worry about
Did you
looking
learn
up
this
keys.
from-
Okay. Did you? What is
Not
the,
really.
What is the performance difference if you're just using like vector addition? Like you implemented vectors instead of using a hash map.
Honestly, it wouldn't be much more on this because we are just doing vector addition. It's just the equivalency comparison. It's the
Okay.
only overhead.
So
Are there any language features about Rust that made this easier or possible that you couldn't have done with C++ or Zig?
I think you could have done it. I think having the smart pointers is the biggest thing here, because the smart pointers are really where the magic is that lets you kind of pass them off and then get them back and still work with them. You could kind of do the same with pointers in C++, but then you lose like the reference counting aspect and you have,
C++ has smart pointers.
I don't know.
Yeah, you just need
much
to
about
not
C++.
use an old C++ book is the important thing.
I mean, you can do all this in C or C++, right? There's nothing too terribly special about Rust in particular.
I hear they're Turing complete, yes.
I was trying to think of how to make that joke.
Yeah, but with this library, it's also, with Py03, it also makes it so much nicer and simpler. I don't know if you've ever written C for integration with Python. It's not as clean, to say the least.
Yeah, that seemed really straightforward, like putting.
And as a final thing, we can actually implement dunder methods. So if inside that impl we implement get item, all of a sudden we can work with it as a dictionary, and we can, do square brackets to extract values at keys, and get most of our work done without ever even turning it back into a Python dictionary.
To avoid the cost of conversion.
What is NumPy written in?
Although
Is it C?
Although I will warn you that like this get item is about twice as slow, 2 times as slow as the native dictionary access, as you might expect, because it has to do
But because it has to
an
go
extra
through,
lookup.
it also still has to go through the Python layer to go through get item.
Well, I mean, ultimately Python's a thin wrapper around C anyways, so
I
it
would
always
not-
has to go
It
through a
is very
conversion.
heavy wraparound. It's got its own bytecode.
Yeah.
But it works with string slices, not just string values,
Yes.
so that
At least a key lookup. And honestly, like this just made it a little bit faster because you could pass a slice as a pointer.
Well, I'm sure it's all that wrapper and
I still want to say, well, what is part 2? What is part 2 of the Rust?
No, actually, I got through all of it.
Oh, you
So we're
said there
good.
was 60 slides.
If you count the transition slides.
Oh, okay.
we're just counting the number on the
Oh,
bottom
yeah.
right.
So I've kind of a larger and broader question. Since NumPy is also transitioning to C out of the hood, just a lower level language, and I have like the general steps of what you did. Where do you think you got the most value by doing something different than what NumPy was doing?
I don't think I'm doing anything different necessarily.
Yeah. So where are the speedups like?
I'm also working. I'm also
working.
working with a completely different data structure though, and the speedups come from NumPy. A supports more operations. B, they support more data types, so they have to do like more conversions. They have to do more checks, things like that. And yeah, I think those are the main things, and that's what this talk is about. It's not like you're going to replace NumPy overnight. It's more about if you have a purpose-built problem, these tools make it easy enough to reach for. that you might actually be able to build a purpose-built solution for your problem that's more performant than what's out there. Because general solutions naturally have an overhead for the generality.
But that's also been a good lesson. It's like, just because you're using Rust doesn't necessarily mean it's going
That too.
to improve it.
Yeah, naive solutions are naive.
And that's like, you didn't have to write a ton of code because the conversion library is already written.
So what does building this look like?
Compiling or running.
Yeah. But I mean, you could do that in a local project, but if you're going to implement it in like a kind of a more broad workflow or have like other people use it in their applications, how are you doing that?
Well, remember the Maturin,
I was gonna say he used
the
to cheat
Maturin
code.
thing just kind of does it for you.
Oh, okay.
See,
So
because
actually
the
never seen
Python developers just install that as a Python.
Yep, they
UV
just
package.
import as a Python package.
it just gets handled by like the setup.
Yep.
And you said you didn't show it, but there was like an import Maturin at the top or import
No.
whatever the name was.
No, the Maturin is only used whenever it's actually building. It's a CLI application, basically.
So do you just like pre-build like wheels for?
Yep. And the Maturin lets you do that in a GitHub Actions workflow, and it just sets it up for you.
Oh.
Does
Does this
different architectures?
underneath the hood, does it compile to a shared object? I think that's all how all of the
I
Python
believe so.
library is.
But yeah, it's there. If you search Red Bear on PyPy.
You just get some asset files out of it, and then that's in your site packages.
No, I'm pretty impressed on how easy it seems because like I don't know, it looks like I think you showed us like the iterations of a couple
Yep.
functions, but so like you just have to write your add function in Rust and then you can call it and like that seems very quick.
Yep.
That seems pretty cool.
This is way overkill, and like I don't know, I've never touched Rust in my life.
Mm-hmm.
Is there like pre-compiler directives in Rust for building for different architectures?
Yep, absolutely.
And then the next question is obviously, would that ever be useful for something where it seems like we're adding a bunch of numbers together, and is there an architecture where it just says like, yeah, I really like to add 4 of these together at once, so can we chunk them?
Like a SIMD operation or
Exactly,
SOC extensions.
Exactly, Cindy.
I mean, there's some Rust crates for maybe like portable SIMD that you could possibly call from Maturin,
Yeah.
but I haven't tried it.
Yeah, it would be overkill for this anyway, is just the thing that came to mind.
No, it would definitely be something to look at. But most Rust crates are callable and usable through here. Just inflates your binary a lot.
Is there any possibility for multiple like Python object wrappers to reference the same underlying vector?
You mean like passing the pointer around to?
Right.
Yeah, I mean you can do the same thing you can do with any pointer in Rust.
But like I feel like you wouldn't want that, right? You would want that like that smart pointer to be only key to that one Python object. Because then you can rely on that Python object.
I mean, I can't think of a good use case where you would want to pass it around to a bunch of things, but like you could. And if you have that use case, like there's no harm in it. That's the whole point of it being smart is like, Rust keeps lifetimes. So whenever all the lifetimes go out of scope, it's still going to get cleaned up. You just have to wait for all those hundreds to release
Well, with Arc, couldn't you get some kind of cycles if you're trying to do like a graph data structure?
it. Yeah, but Rust catches that for the most part.
Well, I don't know for sure. Well, I don't use Arc a lot in my pure Rust projects, but I could see it being useful for something like Python, where you're working with a garbage collected language.
Yeah.
Anyway.
Yeah, is that why you were using an arc there?
Yeah,
Because
you don't have to use the arc either. Like I was just using it because it's the pointer type that Py03 supports. Since Python can execute both like asynchronously and it's garbage collected, so you have to pass off something that you can keep a
Yeah.
reference of.
To work with Python's
Yeah.
system.
And just real quick, because it was pretty early on when we talked about this, the moving from a Python dictionary to the Rust hash map implementation, that wasn't something you had to like write yourself. Like was that how difficult was that conversion? How much code was involved in that, or did the library just
No.
understand?
Yeah,
Like
it just
Py03
does it.
understands that.
Yep.
Yeah, like that's one of the primitives, I think.
Yeah, they support all
Just
the
for all.
primitives. So yeah,
Support all the
I hope you guys enjoyed it.
That was so much fun.